Well, hello and welcome everybody. So this is coming to you over the airwaves. I'm sorry I couldn't be in front of the group in person this year. These crazy times we're in. So I've got a presentation put together here. We'll go through the slides and stuff like that. This will be available, be recorded. So if there's any questions coming up, I put my email in there. If somebody wants to talk about the topics today, feel free to contact me via my email there. Or call me if you want. So I'm gonna just get started. We'll go through the slides. So the topic I chose this year, or I guess the group chose for me, actually, is hydraulic separation. And so what I want to do is go a little bit deeper in the hydraulic separation than just talking about the component and why you would buy it and how you would install it like that. I want to talk about the concept behind it, different ways of doing it, and some of the finer points of it, is just like the title shows there. So well, let's get going. All right, so hydraulic separation to me is really just an extension of primary secondary piping. And maybe most of you know primary secondary. I think probably got popular back in the late 80s, early 90s. It's a concept that was developed by an engineer at Bell and Gossett called Gil Carlson, and Dan Holohan worked for Bell and Gossett back in the day, and he kind of took this concept and ran with it and put it in the news, so to speak, got it in vogue, if you will, and made it popular, gotten a lot of magazines, gotten a lot of training and stuff like that. So he kind of took that concept that was developed, I think, in the 1960s sometime, and kind of brought it mainstream. It was originally intended for big commercial piping jobs where you could take a single pipe or a looping around the building, for example, and just tee into it in various places to put energy into that loop, take energy out of it. So once the genie was out of the bottle, so to speak, people said, well, gosh, we could do this on some of our residential work too. This would save a lot of piping. It would open up a lot of opportunities. And about the same time, a unique thing kind of happened in our industry is these little condensing boilers started appearing on the market, and a lot of those had high pressure drop and still do heat exchangers. So they really benefited by primary secondary piping. So it really kind of addressed two things with one, two birds with one stone, if you will, that we solved some of the problems about not pumping the high pressure drop boilers properly, and also opened a lot of opportunity for these bigger jobs where we had a lot of complex piping, a lot of different loads, a lot of different temperatures going on. So I would highly recommend the book there on the right, Primary Secondary Made Easy. You can find that everywhere, really, at Amazon or online, or certainly over at Dan and Aaron's site there at heatinghelp.com. But it kind of breaks it down into more digestible, understandable drawings and stuff like that. So, but it really is the basis for hydraulic separation, because it involves the same concept of what we're doing. We're just doing it with pipe fittings instead of a single component, is what a hydraulic separator is. So let's just look at how it works, and I think it'll all start to come together for you. So here's what primary secondary piping is in a nutshell. It's where you take a loop of piping, and it's just a loop. Think of it as a maybe a conveyor belt or an escalator where it just keeps going round and round, and you can get on and off anywhere you want. And to get on and off of this loop, this primary loop right here, you have to have a set of closely spaced tees. So basically two tees put together with a close nipple between them, for example. And so what's happening here is when the circulator is running here, let's call this the primary circulator. It's running, it's moving the conveyor belt, so to speak. And now I want to jump off the conveyor belt with some BTUs and go out to a heating load here. Let's call that a little fin tube load or something out there. So what I'm going to do for that load is I'm going to size this circulator for that load and only for that load. So let's say I need 5 gallons a minute out there, and this circulator is moving maybe 15 gallons a minute around the conveyor belt. I size this circulator to pull off just that amount of energy, that many BTUs or gallon per minute, however you want to look at that load. And then the rest of it continues on to the next load. So I'm just basically sipping off a little bit of energy. Now, the only way that can, and the only way that will work, is these tees have to be sized properly for the flow rate of this pump and for the flow rate of the secondary, the branches, so to speak, going off it. And obviously installed properly, they have to be right next to one another. You can't have one here and one 6 feet down the road, or the other one on the return side. The concept here is that water can flow two different directions between these two tees. So if I've got 15 gallons a minute going through here, and I take 5 gallons a minute off, 10 gallons a minute is going to continue on until this branch comes back into it, brings the 5 back into it. Now I continue on as 15 gallons a minute. So it really did open up a lot of opportunities to mix and match different size pumps, to mix and match different temperature loads coming off it. It just became like a giant transmission, if you will, in our piping system that allowed us to switch different gears and do different types of things. So there's the concept right there, is primary, secondary. There are some rules, I think. Let me look at my slides coming up. I'll show you some requirements for the spacing between various sets of tees. So there's a set of tees. If I wanted to put another set of tees in here, there's a requirement for the distance between, and we'll get into the details of how to pipe that a little bit. So obviously in this drawing, there's components missing. I didn't put an expansion tank and an air purge. I was just trying to keep it a clean primary, secondary drawing without complicating it with some of the other piping components in there. One of the questions you're going to ask me is, okay, where would I put the expansion tank in there? And I think a confusing thing in the industry still is which is the primary loop and which is the secondary loop here. And my understanding and the argument that I'm going to go with, and the story that I'm sticking to, so to speak, and I got this from just chatting with Holohan recently, actually. He said, wherever you install the expansion tank, wherever you want to establish the point of no pressure change, he said, that becomes the primary loop. He said, if for whatever reason you were to put the expansion tank connection over here, which you could, then this becomes the primary loop. Even in this drawing, I'm showing as a secondary loop. I don't have an expansion tank, which might further complain that explanation, but he said really the primary and secondary loop is determined by where the expansion tank, which is established in the point of no pressure change, we'll talk about that a little bit more, is tied into one or the other loop. So sometimes the boiler is in the primary loop. And this one here, I consider the boiler in the primary loop because I'm just flowing right through it. It's a high capacity boiler, low pressure drop, maybe a cast iron boiler or something like that. So I don't have a lot of pressure drop, so I can just pump right through that boiler and make that part of the loop essentially. So just know that when you look at a drawing, or you go to a job site and you're troubleshooting, you're working on it, I guess ask you to first look and see where the expansion tank is, so you can, number one, can establish your point of no pressure change, make sure all your circulators are pumping away from that, and that's going to determine which is the primary or secondary. So if you're talking to somebody explaining that, that's kind of the, let me move my toolbar out of the way here. So here's an example of, again, best practices. There is no code that I've been able to find. There's no law, there's no police out there that are going to check something like this. In fact, I would imagine most of the inspectors don't even understand this piping concept here. But here's, I would call them best practices or rules of thumbs. The amount of piping that you would want to have in front of the closely spaced tees, the close nipple behind them, the distance before you have a fitting or another set of tees. So basically what we're showing here is 8D, which means 8 pipe diameters. So if this was 1-inch copper pipe, then we'd have 8 inches of straight pipe upstream of the first takeoff. I like a close nipple in there. If it's a threaded connection, a close nipple, if you're sweating copper, pressing the fittings together, as close together as you can get those. You can spread them out as much as 4 pipe diameters. Again, I could have 4 inches between there. It's still going to work. I don't like to see them get out to 12, 18 inches, because what'll happen if I get these two tees too far apart, as this flow is going through there, it says, there's a little bit of flow resistance going through there. I'm going to make some of my flow go up through this branch here, and you can get what's called ghost flow. You could get a little bit of flow going out to a secondary when you don't want it. Now, you could eliminate that by having a check valve on your pump, or, check on your whatever you're going to use off the secondary tee here. You might add a second check valve on the return side, so you have absolute 100% shut off on both of those. So if there was some reason that you're going to get a little bit of a flow encouragement out to the secondaries by having too wide of a spacing here, check on both sides of those would prevent that. But I mean, just get in the habit of following these guidelines. This will work. You won't have problems with ghost flow and other things if you adhere to the suggestions or the recommendations that we show here for the distance. So obviously if that's a 2-inch pipe, 8 times the diameter 2, you'd want 16 inches there. Now I know you're going to tell me you see jobs out there where they've got an elbow right against this tee and they've been working for 20 years. Yeah, you know what? They probably will, and they probably do. It really depends on what the resistance is out in the secondary loop. If for whatever reason this was a low pressure drop loop out here, you'd have more potential for that flow from this primary to bleed off into those secondaries. If there's a path of least resistance basically for the water, it's going to follow that, or it's going to take that. So here again is an example of a high pressure drop boiler. And what would happen with these when they first came on the market is people would go to a job site and they would say, well, we're going to take out your cast iron boiler and we're going to replace it with one of these new high efficiency boilers. You're going to get higher efficiency. It's a smaller box. It's got outdoor reset. It modulates. It has all these really nice, unique features that the homeowner might want. And they would take that cast iron boiler out and they would pipe the new one in exactly like the old one went out, which is just right through the boiler. Well, sometimes this would work, sometimes it wouldn't. The issue would come up that you had to make sure that these circulator pumps all had enough, could develop enough, had to overcome the pressure drop in that boiler. If you got it right and you had this on maybe speed 3 on a variable speed circulator, you might get away with that, and a single pump like this could work. But if that was I don't know, maybe a 007 or something with a low head circulator, and you had more pressure drop through the spoiler than you could overcome with that, well, the boilers would go into lockouts, they would overheat, they would bang, they would crackle, they would go out on lockout. It just created all sorts of problems. So that's why this type of boiler really needed to be tied in to a system with primary, secondary, or, as we'll get to here in a second, hydraulic separations. In the early days, the boiler manufacturers weren't even making us aware of that. The drawings were coming out and they were just business as usual. Some of those lessons I think we had to learn and train the boiler manufacturers to start putting drawings in there that represent what the way the boiler needs to be piped to work properly, to ensure that it was going to last a long time and not keep throwing out nuisance lockout code. So the primary, secondary, we'll get into more of those schematics as we go here, but this is an example. So we actually did an hydronics journal that we called best practices. And what we did in there, and this drawing comes right out of that, is we took the 6 or 8 most common mistakes that are made when people try to do primary, secondary piping, and we put a big X through them, because we get these pictures or drawings sent to us all the time saying, I'm having trouble with my boiler, and we get a picture that looks like this. And so what we did is we tried to take the picture of what doesn't work and then give you the picture on the next page of the correction for something like that. Because somebody would look at that and say, well, I got closely spaced T's. You told me to put 2 T's together, and there they are, closely spaced T's, closely spaced T's. Well, you have to go out of one and right into the next one. You can't go out of one and go into a second T somewhere else in the piping. They have to be supply, return on these sets of T's. So this could be corrected by putting the return there, and you'd have primary, secondary, but you still might not have enough flow for a high pressure drop boiler. So let me show you some better suggestions for that, or ideas on how to pipe that. I want to talk about check valves a little bit, because there's a couple of things out that I've seen over the years, and I've made this mistake myself of misapplying check valves. The most common check valve that you'll see, and if you go up to the counter and ask for a check valve, there's a pretty good chance you're going to get this type of check valve, and this is called a swing check. And basically the way this check valve operates is this little flapper in here. When there's flow coming through it, the flow pushes that flapper up into this little space, this little hiding space that the flapper can go open and flow can go through it. When the flow stops, the flapper just closes down, and it prevents any ghost flow or any flow that you don't want from going through it. A couple of things about this type of check valve is, number one, it really would like to have a pressure differential to make sure that this gate closes and seals tightly, so you don't have any what we call ghost flow going through it. And if you look at the way this type of check valve works, it's really just the weight of this check valve that's closing that off there. And so the right application for a check valve like this would be, well, think of a sump pump. When the sump pump is running, the gate's open like this. When the sump pump shuts off, all the piping above it has pressure in it that closes that gate, and it makes sure that you get a tight seal and you've got a check. Well, think about a hydronic system. When the pump is running and the check is open, you've got a little bit of pressure opening that gate because you got the pressure differential that the circulator is adding to it. But when that circulator pump shuts off, you've got the exact same pressure on this side of this wafer as you do on the other side. You've got the static fill pressure that this valve is seeing. There is no additional pressure on this side in the closed loop hydronic system to make sure, on this side I should say, to make sure that gate stays tightly closed. So, you can get away with it sometimes, but it's not the best check valve for that. Some of them can be mounted vertically and horizontally. Some of them have to be mounted in this position. Make sure if you do see one of these installed that the manufacturer allows it to be installed vertically, for example, if it's not rated for that. There's different patterns, there's Y patterns, there's different configurations of this type of swing check valve, and they have different installation requirements. So the other options are this you've probably seen for years, the boat anchor, we call it a flow checks. It's just a weighted plug in here. It's got a plug in there that weighs about a half a pound. So you got a half a PSI shut off. It's a 1-inch diameter. So it's the weight of the plug inside here that when the flow stops, the plug settles down and it shuts. And they work fine. I mean, they've been around for years. They work fine. You can manually, with this lever, force it open. If you got a job where you've got a power outage, and you want a little bit of heat to come out of the boiler without the circulator pump running, you could go over there or have the homeowner just screw this, I think, counterclockwise, lifts that plug up in there, and then you'll have flow going through there. By the way, if you get on a job troubleshooting and they've got a ghost flow situation, make sure that somebody hasn't opened this and left it open or didn't realize that that valve needs to be screwed clockwise so the plunger or the plug in there is working under its weighted condition. I think better yet is this type of check valve, and there's different brands out there. We make one at Calefi, Combraco, Watts, pick a brand. Pretty much everybody has what's called a spring check. And difference inside a spring check is, like the name implies, there's a little spring that actually pushes the check valve closed. So in addition to have a spring to make sure you've got good closure on that when the circulator starts, it also has a better shape to it. You can see this isn't a very flow-friendly shape. I'd rather see like a conical shaped opening in here and a conical shape to this little flapper in here, so when it closes you got a nice tight seal in it. It's going to be a little bit more friendly to flow. So you've got the right spring in here. Typically these are going to be either a 0.35 or on the larger size you'll have a 0.50, which is half a PSI pop is what we call it, the pop pressure of that valve. So even the smallest little circulators that you might be using out there have sufficient pressure to pop open this type of check valve. This one happens to be nice in that you've got the union connections if you want to take it out and clean it out or service it or something like that. One last thing I'll say about this swing check valve is when you buy one of these, you should really buy this valve based on the CV number, the flow rate of the valve, not the pipe size, because what has to happen is the CV rating of this valve, meaning the gallons per minute that can flow through that valve with a 1 PSI pressure drop, that's rated with this gate fully open. If you don't have sufficient flow, let's say you put a 2-inch check valve that's rated for, I don't know, say 40 gallons a minute flow rate, and you only have 20 gallons a minute flow rate going through it, this check gate might not be fully open, and then they can chatter. So the gate's somewhere in limbo here, somewhere between closed and open, and it's just flapping around in there. So if you do use this type of check valve, make sure you're sizing it for the flow rate, not for the pipe size. And sometimes, even though it looks odd, you might have a check valve like this that's 2 pipe sizes smaller than what it's connected into it, because that's the proper flow rate for that check valve. So, and they do have a high flow rate because you can see they've got a nice wide open flow passageway through them when the gate is all the way in its its hiding place there in its full open position. This I put up there, I don't know if you can read that, is an example what can happen with a pipe where you can actually have flow going in 2 different directions in a pipe. And sometimes you can get ghost flow where hot water can go up. Usually the hot water will go up the core of the pipe and the colder water will come down on the outside of it. So you've got a bedroom on the 3rd floor of a building and they say, you know, my bedroom keeps overheating. The pump is off, but I'm still getting warm radiators or warm baseboards up there. What's going on? Well, this could be happening if you don't have check valve protection on those risers. And let me go back a picture. You're going to see that most often whenever you have a horizontal pipe like this with hot water in it and you've got vertical takeoffs. That really encourages thermal siphon, because hot water, like hot air, like a hot air balloon, wants to go up and cold water wants to come down. And that's how the old gravity heating systems work, is the hot water went up by the buoyancy, the hot water being lighter went up, the cold water came down, and you circulated through your radiator just based on that temperature differential. So if you have a path of least resistance like this, which is vertically off this horizontal, and you've got a temperature differential, which you do, you've got hot water down here, you've got colder water in your radiators, you can actually get that little thermal siphon, and you can actually get it through a single pipe. We call it back end flow, and it's called ghost flow sometimes, which is just a small flow. It could take weeks, it could take months for that to show up as an overheating condition, but it's caused by a 2-directional flow in a riser pipe like that. All right, what else did I have over here? I think we talked about the ceiling. I think I covered all that. All right, so let's talk about the variations of primary, secondary. So the first thing that showed up in all the magazines as we started about primary, secondary is what's called a series primary loop. And so what they said is that, okay, just make a loop around your building, maybe just in your mechanical room on the wall. This could be 5 feet long, this loop. It could be hundreds of feet going around the building. So it has to be a loop, and it has to have a circulator pump in that loop that's moving this, again, let's just call it a conveyor belt. It's moving this conveyor belt all the time. This was a little bit tricky to size this circulator, because think about this being just 8 feet of pipe in a mechanical room, and this boiler is maybe, let's call it 200,000 BTU. I want to move about 20 gallon a minute around this loop. Try and find a pump that moves 20 gallons a minute at a couple feet ahead, because really that's all that these couple elbows and this pipe is presenting as a resistance to that circulator. So it was kind of an odd pump to, most of them were probably running off their curve, because you didn't have a lot of high flow, low head, virtually no head circulator choices out there. So be that as it may, we sized that circulator the best we could to move the gallon per minute that we needed around the conveyor belt. Now this boiler manufacturer is going to say, well, I want 18 gallons a minute going through my boiler, when it's under high fire conditions. So this circulator would be sized for that flow rate and the pressure drop that this little heat exchanger presented when it was flowing at that 18 gallons a minute. A lot of the boiler manufacturers actually did us a favor and would tell you, okay, here's your choices of circulators. There's a couple different brands typically, and they would give you the model number and the speed that they wanted you to put it on. Say, pick that circulator, put it on that speed, pipe it this way as you see it in the drawing, and you're going to be fine. So that's great. Okay, we're moving along here. Things are getting better. Here's a couple things that it didn't show up in the magazine. It wasn't explained in any of the things that I read. Maybe I missed it, but they didn't warn us about a couple things when you start putting a bunch of T's together like this on a series loop. And that being is, let's assume the water is going to come out of this boiler at, pick a number, 160 degrees. I've got 160 degree water there. I've got 160 degree water there. I've got 160 degree water here. And now out of this fluid going around here, I'm going to take, I don't know, call it 8 gallons a minute. I'm going to pull 8 gallons a minute going out to a load here on maybe, the upper level of a floor of a home or something like that. And so that water is going to go up to that load at 8 gallons a minute at 180 degrees. It's going to go through the load, the radiator, the radiant floor, whatever's out here. And it's going to come back at a lower temperature, because it's going to drop, 10, 15, 20 degree delta T, depending on what you've sized this for. So this is going to be, let's say, 140 degrees coming back. And so now I got 140 degrees here. I've got 180 here. That 140 is going to blend with this 180, and I don't know if you can tell by the color, the loop changes. Now I've got a lowered water temperature going to my second load. So if this load is looking for 160, 180 degrees like it is at the first one, it's not going to get it, because you've blended down that temperature. And now the further you go around the loop, the worse it gets. I mean, you could go down to a point here where the water is going to come back at room temperature, because you don't, that blending has caused that hot supply water to be blended down, blended down, blended down. So then the word came out, well, that can happen. What you need to do is you need to take your hottest temperature loop off first, take your medium temperature load, and then your lowest temperature loads last off the loop. Well, what if I've got a job where I need all the same temperature? I don't have multiple temperatures. I want the same temperature going to all my fin tube, to all my radiators, to all my air handlers. How am I going to do that? Well, there is a way you can put a crossover here with a balancing valve, and you can balance that every one of these would get the same flow under the operating conditions of all of them run at the same time. It got really messy. Nobody knew how to set the balancing valve, how to size the balancing valve. It just ended up to be, people said, forget it, this isn't working for me. I've got to come up with another plan. So this series, if you understood this and you could work around that and you could use variable temperatures, you went around the loop, yeah, it worked fine. I mean, it solved the hydraulic separation issue. It made it so you could size your circulators properly for every load. It did solve a lot of the problems that we were having when we started doing multiple load big buildings like that, but it brought some other baggage along with it. And mainly it was the temperature drop as you went around the series loop there. So the other thing you'll notice just looking at this drawing, a lot of pumps in there. We used to be able to do those with a boiler and one pump, and now you're telling me I need a boiler pump, I need a primary pump, I need secondary pumps. Guys said, well, this is getting crazy. So maybe it wasn't the best application for all the jobs out there. If you had to provide this separation, yeah, you kind of had to do this. You had to have some kind of hydraulic separation between these circulators and these. So this was really, in the beginning, about the only option we had. So we looked at that, and interesting about all of this for us, for me, being a Cleffy employee, is this boiler had been around in the European market for quite a few years before it made it across the pond to the US market. So we had developed some products, and we understood some of the issues that were going to happen when you start piping these boilers the way you used to pipe in a cast iron boiler, which was the lack of separation. So we had identified some other piping schemes that would work with this boiler, and we said also develop some products called hydraulic separators that would solve all these problems that you're having right here, and actually add a couple nice features to it. So let's go through a couple more piping fixes first, and then we'll talk about hydraulic separation. So look at this drawing right here, and I want you to see a couple things. Is number one, I've taken that series loop connection out of that, let's call it the primary loop. You can see I've disconnected them. I no longer have a loop, but I do have a primary secondary connection. I have a loop here, so when my boiler is running, I've got flow going through my boiler at the proper flow rate that this guy, the manufacturer, tells me he needs or wants for that boiler. Size that properly, got my closely spaced T's. Everybody's happy over here. I've taken one pump out of the equation because I don't need a pump to move the loop around. I've got my boiler pump moving this. I've got my distribution pumps that are going to move through my loads. And the other thing that I've cleaned up for you is I put all my loads in parallel now. So every one of these circulators is going to get the exact same temperature. This one, even though I'm showing here different size circulators, different flow rates, different GPM on these circulators, just by the size of the pump icon there, they're all going to get the same temperature. Now, that being said, it's going to be a blended down temperature from what you're seeing here, because this cold return is still coming back. It's going to blend with, again, let's call that 180 coming out of here, and it's going to blend this temperature down, and you can calculate what that temperature blend is going to be based on the flow rate going through this and the temperature coming out of that boiler and the flow rates over here. It's called the mixed temperature formula. You can predict what that's going to be. So it did clean up a couple things. It cleaned up having to size that primary loop pump. It took away my series temperature drop from every takeoff, every takeoff, every takeoff, and it just cleaned everything up. Still had my hydraulic separation. Everything was fine. I had some options for where I could put my expansion tank, because this large piping here becomes part of the point of no pressure change. This expansion tank connection right here establishes what's called the point of no pressure change. So if you look at this drawing, the point of no pressure change continues on through this header, or through this piping, this header, whatever you want to call it, through this loop. This pump is pumping away from the point of no pressure change, even though this could be 10, 15, 12 feet away from it, as long as I size this appropriately, which would be for the flow rate of all the combined of all these secondary circulators added up. Let's say they add up to, I don't know, 20 gallons a minute. I would size that at 1.5 inch piping. Now I've got enough flow capacity through that to handle the flow rate, and also establishes my point of no pressure change. And by default, through the primary secondary T's, through the oversized piping here, the properly sized piping here, these pumps are pumping away from this point of no pressure change here, even though they're quite a ways away from it. This point of no pressure change is established through here to every one of these pumps. This pump is pumping away, this pump is pumping away. You could, in some cases, move that expansion tank here. This pump would be pumping away from it, but you'd have to make sure that the sizing here was adequate, that these pumps could see that point of no pressure change. At the end of the day, this is a really nice place for an expansion tank for a number of reasons. I've established a good point of reference for all my circulators, but I've also put my expansion tank in a lower temperature water right here. So maybe the diaphragm lasts a little bit longer if it's seeing, return temperature water as opposed to the higher temperature water. I mean, in a perfect world, you're not sizing this for 180-degree temperature application anyways, or it's not going to condense, calling this a condensing boiler. So a smaller footprint here. You can see I don't have to have a place to put that big series primary secondary loop and connect it together. I've taken a little bit of labor out of the job. I've taken a pump out of the job. This is a really nice way to do primary secondary piping to solve some of the problems that we had with the previous series loop drawing that I showed you. Now here's another variation of that. What I like, let me go back one more. What I like about this is I could put this in a really confined space. In fact, I could move this directly below the boiler, and I might be able to get a boiler and the secondary loop and all these secondary pumps in like a 3-foot wide closet. Not that you'd want to do that, but sometimes that's what we're left with. That's the nice thing about this. I can really scrunch this down. I can really get that into a small footprint in a tight mechanical closet or room. I think I might have a picture of one of those coming up. This one here, I'm essentially doing the same thing. I call the previous one a horseshoe because it's shaped like a horseshoe. I call this a moose antler because it kind of looks like the antlers of a moose. I'm doing the same thing here. There's my primary secondary. Even though I don't have a loop over here, I have a primary secondary connection via the closely spaced tees. I've got parallel connections, so I've got the same temperature going out to all my circulators. I just made it, maybe if I've got all my distribution going above me, maybe this is a cleaner way to pipe out of this by having everything pointing up vertically like this. So it's just a variation of that previous horseshoe where I put a parallel primary secondary loop in instead of a series loop. And maybe this works on a room where I've got a lot of real estate that I want to spread out my pump, so I've got a little bit more serviceability, a little bit more room to stack a bunch of circulators on that. So horseshoe, moose antler, they're both a version of secondary, primary, secondary piping without the series loop baggage, so to speak. All right, here's another, this is a drawing we see. This is a job site that we visit. The guy said, well, I did the primary, secondary, closely spaced tees just like the drawing showed, but he didn't use them properly. He's got them all in a row. That's better than the first drawing where they had some down here and some there. But they have to be the first one. And by the way, the pump always has to be on the first one. If the supply direction is this way, you want to pump away from this loop because that's how it's going to see this point of no pressure change. In this case, through the cast iron boiler, wide open boiler, no pressure drop, very little. Point of no pressure change is established through here to this pump and also to the secondary pump. So this pump needs to be on the first tee. This tee needs to be the return for this pump here. It can't be the next set of takeoffs of that. So all I'd have to do in this drawing is I'd have to move this connection, this return line to this one, move this pump over to here, move that connection, return to there, move the third pump down to here and the return there. So this is a salvageable system. At least the closely spaced tees are in there, and if they're sized proper for the flow rate of that loop, then this is a fairly salvageable job, but it's not the proper way to use primary, secondary. You got to have supply, return, supply, return, supply, return. They've got to be in that sequence. So there's another one. This is similar to the first one I showed, thought that, I got a primary loop. There it is, a loop just like you told me. I got a conveyor belt. It's working fine. The boiler's happy. Everything's going, but I'm not getting proper heat out to these things. In fact, you can actually have reverse flow going through here. When one pump is running, it can be pulling backwards from this one. So this isn't going to work. Check valves aren't going to fix it. This isn't the proper primary, secondary. All this is calculatable, if that's even a word. You could determine, if you figured out the pipe sizing and flow rate here, you could determine what the pressure drop is between all these and predict if this would work or not, but it's not a true primary, secondary. You might get away with it if all the stars lined up right. You could say, well, I've done this and it's worked. That's possible, but it's not giving you the benefits of primary, secondary piping. Why it would work in this case here is I've got a low pressure drop cast iron boiler in my loop there. This boiler isn't sensitive to flow rate. In fact, I could probably run this boiler without even running that circulator there. We used to run these boilers without circulators and gravity systems. As long as it's got, protection, you might get away with that. I see this a lot, and not my favorite thing. It does work, it can work, as long as I have this distance close enough. The issue I've got with a ball valve between them, and I know why you put them in there, it makes it easier to purge that loop. Just shut that valve and you've got a nice purge path through there. But even a full port ball valve, if you look at the pressure drop through a full port valve, it shows up as probably about 3-4 feet of equivalent piping length when you go to one of the calculators, when you size your equivalent length by selecting the fittings. So even a half a PSI pressure drop between these tees could in some cases cause ghost flow out to that. Yeah, you could check this and you could check that, but I think a Webstone valve, for example, over here with its own purge port is a cleaner way to do this. It's going to be a smaller, probably less expensive valve, number one, and it gives you the ability to just purge this loop without having to put a valve in there that somebody might inadvertently close one day. They say, well, wait a second, how the heck is this going to work when that valve's open? And somebody someday comes and closes that valve thinking you made a mistake, and now you've got problems. So I don't know. I don't like to see a valve between the closely spaced tees just for the purpose of making a better purge arrangement. Just put like I say, a purge specific valve over there and accomplish the same thing, and the temptation of somebody shutting that valve goes away, or the potential to have a little bit of ghost flow from the pressure drop. And if this were an 80 port or reduced port, 80% flow ball valve, then you will have ghost flow conditions there. So it would have to be a completely full poured valve, but even that, there is some restriction through a full poured ball valve. Yeah, here it is. We talked about this one, I think, when we were showing the expansion tank connection on a previous couple slides. The circulator has to be on this side of the primary secondary takeoffs because that's where it's going to see the point of no pressure change. In this case here, I'm pumping at my expansion tank at my point of no pressure change. So easy fix there, just swap the pump, keep the check valve in the pump like we're showing here. Keep your Webstone valve there for purging. I like that application better than between the T's. So it's got to be on the first branch or the first set of the closely spaced T's. So I want to talk a little bit about hydraulic separators. So we came out with this product. We said this is going to solve problems of guys not quite understanding the concept of primary, secondary. You can't screw up a hydraulic separator. Well, maybe I spoke too soon on that. Here's an example of somebody spending a lot of money on this hydraulic separator to accomplish primary, secondary, because really that's all this is closely spaced T's here, closely spaced T's here. And for some reason, for whatever reason, they chose to connect the secondary side here with a valve. I don't know why there's a valve in there. And they chose to put a primary, secondary T connection here. So essentially, this is just an air purger, is all this is really adding to it. So I'd like to find a person that piped that. Maybe there's some magic that's going on there that I don't understand, but it's not the proper way to use a hydraulic separator device. And it's I'll show you how a separator is designed to work and why that can't work. So basically all I've done with a hydraulic separator is I've taken those primary, secondary T's and I just put them into a container, a box, a shell, call this whatever you want. It's just a piece of pipe. And now there's my flow path for my boiler. There's my closely spaced T's. If you turn that outside, it's just two T's together, and also on my secondary side. The nice thing about this is, number one, it cleans up your piping a little bit. I don't have to buy the T's. I don't have to pipe them together. I take a little bit of labor out of the job, but I can also add some additional features of an air separator. I don't have to put another, call it what you will, a spiral band or whatever brand you like to use out there. I don't have to have a separate air separator in here because this becomes an air separator just by the default. When you make it a separator for hydraulic separation, you've got a wide chamber in here, which turns it into a very nice air separator. The same thing for dirt. I don't have to put a Y strainer in here because this is going to be a dirt chamber. As the dirt particles come through here, the velocity drops to almost zero under some conditions here. The particles fall out, and then I can just come back, open this ball valve, and I can blow out the dirt and debris that settles into that. So just think of this as primary, secondary in a tube or in a box or in a container. It could be round, it could be square. There are a few things that are critical. If you want to build one of these your own on the job site, I'll share some of the engineering that goes into sizing or building one of these hydraulic separators. Now notice where I put my expansion tank here. I don't have it on the top where you'd typically see an air purge and expansion tank here. I put it here because, again, with a low pressure drop boiler, this would have to be a cast iron or any low pressure drop boiler, electric boiler, whatever it might be. My point of no pressure change goes through this pipe, goes through this wide open pipe space here through my boiler, and it establishes the point of no pressure change for this circulator through the pump, through the boiler. And these secondaries, in this case, or let's call them secondary loads, not the secondary side, because again, I told you the primary, secondary is determined by where the expansion tank is. This is my primary loop. These are my secondary takeoffs, but they are seeing the point of no pressure change through this pipe, through the hydraulic separator, through this piping, through the boiler to here. You'd think that the expansion tank would want to be or have to be up here. If you put it there, this pump is going to pump at it. So I've just established my point of no pressure change for multiple pumps, even though they're not next to one another, by going through the boiler, through the piping, through the hydraulic separator, pumping away, pumping away, pumping away at all these connections, as well as this pump here. All right. So here's your two options for piping a high pressure drop boiler. Is you've got to do primary, secondary, and most of the boiler manufacturers now are including this, thank you, in their installation manuals. They show you a primary, secondary with closely spaced T's. They might give you a pump sizing for this boiler over here, which would be nice. Some will even show you the pressure drop through this boiler, so you could actually plot a system curve over the pump curve and get an operating point for that circulator, which is another nice thing. And this is the other option, a hydraulic separator. And so what the separator will do, you would buy this, you would mount it on some unistrut, mount it on the wall, make your connections to your boiler over on this side, your loads over here. I could have multiple circulators. I could have one circulator with zone valves. There's different ways I could pipe my secondary on this. But now I've taken this component, and this component here, the closely spaced T's, and I've just put them all into this device right here. So I've taken some part, taken some labor, I've taken some cost out of the job. Everything in the little cloud here is built into, included inside the hydraulic separator. Theoretically, if you size this properly, you won't have any pumping problems ever. I mean, somebody could come and change this, put the wrong size pump in there, they could change the pump here. It's still going to work as long as this separator is sized for the gallon per minute of this system. And now when you buy one of these, what you need to know is what is the highest flow rate in the system. So let's say for whatever reason, I've got a boiler over here that needs 20 gallons per minute at high fire condition. I got to move 20 gallons a minute through that boiler to get all the heat out of it that it's generating. So I'm going to size this pump and this piping for 20 gallons a minute. You could have a job where the load side is only 10 gallons a minute. For whatever reason, maybe they're going to add on to this in the future, something like that. You have to size the hydro separator for the largest of the two loads. Don't add the 20 gallons a minute here and the 10 gallons a minute and go and buy a hydraulic separator rated for 30 gallons a minute. It's the larger of the two sides. So if this is 20, that's what you want to size it for. Now you could come across an application where the boiler, maybe it's running a high delta T and I'm only moving 10 gallons a minute through the boiler, but I need 20 gallons a minute going out to my distribution. That's my larger load. Then my distribution side would be 10 gallons a minute. I would size the separator to that load. Again, not the combination of the two, not the smaller load. It's whichever of the two. Now, obviously, in a lot of cases, it's going to be the same. If I've got a 10 gallon a minute flow rate over here, I've got a 10 gallon a minute flow rate over here, I've got a 10 gallon a minute hydraulic separator is what I need. So don't add them. I guess the bottom line now is don't add your load side and your boiler side and size your separator to that. I mean, it wouldn't hurt to do that. I mean, it'd work. It's just you're going to be buying more separator than you need for the job. So you're kind of throwing money away. All right, so let's just jump inside a hydraulic separator, and I think all this will come clear on how this works, why it works, and how you could create one of these your own. So let's just use an example of 40 gallon a minute flow rate. So that would be probably 2-inch pipe size for 40 gallons a minute. In fact, that's what I'm showing here is 2 gallons a minute, or a 2-inch pipe size would handle 40 gallons per minute. So the magic, or the engineering, let's call it, not magic, that term seems to tweak a few people out there. The concept here is this tube, this space in the center has to be 3 times the size of the space of the pipe coming into it. So if this is a 2-inch pipe here, and you could calculate the area of that, this here would have to be a 6-inch diameter. And by making that a 3-to-1 relationship, making this tube in the center 3 times the diameter of the tube coming into it, it assures that I've got enough space for flow to go through this path right here without encouraging or causing any flow to go out here. And essentially what I'd like to have happen in here is I'd like to have the flow velocity drop to near zero between this connection here and this connection here. Obviously, it can't get to zero ever. Even a 1 gallon minute flow rate is going to have some pressure drop. But you can see in this example here, if I had a 6-inch diameter tube here and I've got a 2-inch diameter copper coming into it, and if I'm flowing 40 gallons per minute, look at the flow velocity inside this. It's a 1/2 foot per second. The water is barely moving through there because it gets to a wide spot, a wide chamber in the road, and that velocity drops down because it has that additional capacity or that additional size in there of a 6-inch pipe, 2-inch pipe going into a 6-inch pipe, velocity drops. And that's how the hydraulic separation can work. Now I could take off whatever I needed on the secondary side. I could take a 40 gallon per minute or gallon per minute load off of that. And what will happen is the flow is just going to go straight through the separator. There will be no movement from the top to the bottom because I got 40 gallons a minute coming in, 40 gallons a minute going out. It's just going straight through there. It doesn't even understand there's a separator in there. Still get my air removal up here, still get my dirt particle removal down here. It's still an air and dirt separator, but when the flow rate is equal on both sides, it's really just a flow through on that the device. Now that rarely happens unless you had a fixed speed pump here and a fixed speed pump here and a single load over here, maybe a snow melt or something like that. I would have that condition. I might still want a separator on that. If I've got a high pressure drop boiler, I want to make sure that I've got the proper flow. Most of the time, one of two things is going to happen. I'm going to have more flow rate going through the boiler than I do on the secondary. Then there'll be some blending going on in here, or I could have the opposite happening. It's unusual. It's not impossible. It's unusual to have exactly the same flow rate on both the A and B side of a separator. And that, especially if you're using variable speed pumps, a lot of guys are using delta P or maybe delta T pumps. So on my load pumps over here, if I've got variable speed pumps going over here, then obviously my flow rates are going to be ever changing going through this. Even if I had a fixed speed on the boiler coming in at 40 gallons per minute, as the load circulators turn on and off, or if they modulate up and down based on a delta P or T function, obviously that flow rate changes. And that's really why you want to have a hydraulic separator. So if I'm going through it, maybe some days I'm going through it 40 gallons a minute on my load, some days it's 20, some day it could be 5 gallons a minute flow rate if I've just got a small load column over here. This space, this chamber, this separation in here assures that those pump conditions are always going to be such that no pump ever gets starved for flow. The boiler's never going to get starved for flow. So I've just made it simple for installers to do primary, secondary without having to build the T's, without having to calculate the sizing and the temperature drop between the series. I'm going to get if I put multiple circulators out here on the secondary side, let's call this, they're all going to get the same temperature as the flow coming into it. Now it could blend depending on what's coming back here, and it could change, but they're all going to get the same temperature because these pumps would be in parallel to one another, not in series like the very first series primary loop we showed where the closely spaced T's blended the temperature down to the next one downstream. So now another way to do hydraulic separation, we'll pull one more component in here, is with a buffer tank. Because if you think about it, a buffer tank is really just a supersized hydraulic separator, but it brings in a couple more advantages in that if I've got a small fluid content boiler, some of these new boilers only hold about a gallon and a half of water. By connecting it to buffer tank, now I turn that low capacity or low I say low volume, but low fluid capacity boiler and the high capacity boiler. I'm basically turning it into an old cast iron type of boiler. There was advantages to the cast iron boilers. Number one, they held a lot of water. They could hold 10, 15, maybe 30 gallons of water. They had a lot of thermal mass, and the cast iron might weigh, what, 200-300 pounds for a 150 BTU cast iron boiler. So I had some buffering. So when I started going to low thermal mass boilers, low water content boilers, thin metal boilers that weighed 100 pounds instead of 300-400 pounds, I took away some of that buffering that was built in my boiler, and I could start to have issues with short cycling on my boiler, number one. And also if I had varying loads, it made it a really awkward condition to operate a boiler, especially if it wasn't a modulating boiler, without having that buffer capacity that I've taken away by switching to that type of boiler from an old cast iron boiler. So there's conditions where an installer might say, you know what, the job requires a 200,000 BTU boiler at design condition, but I've got 25 heating zones coming off, and then some of them are only 3,000-4,000 BTU loads. What's going to happen to that boiler? Maybe it can modulate down 10-to-1, maybe it gets down to a lower turn down rate where I can accommodate some of the zones. But if I get down to those micro loads, you're still going to have issues with that boiler cycling on and off more than you would like or more than you'd want. And you've got component wear, you've got noise. It's just not a good operating condition. So that's where buffer tank can come into the equation, and it can take away some of that cycling issue. It can give you a little bit of parking space so that boiler doesn't have to fire. A buffer tank might be used where you've got like maybe you've got electric boiler and you've got off-peak rates, and you want to charge up this thermos bottle, let's call it, on low peak off-peak hour rates, and just sip off this tank through the night and or through the day, and then kick that boiler back on and when the rates are down low. So people use them for different applications. Typically, it's to take short cycling out of a microzone system. More often on like a wood-fired or pellet-fired boiler, they're trying to get a little bit of off run time, so they're not feeding wood to the boiler all day long. They can park some of that energy into a buffer tank. So I want to show you a couple different ways that this can be used. So if you look at this here, this is just a supersized hydraulic separator. And by doing that, I've got great air elimination here. All I need to do is put a flow type of air vent on the top of that. And as my fluid comes in here, that velocity is going to slow way down in a big chamber like this. That air is going to go up to the top of this dome shape up here in this buffer tank. And I'm going to have really good air separator. I'm going to do a little demo of that with a clear pipe tuning the heating help here in the next week, and if you're around, that would be July 13th. If you get to this before then, you'll see a little demo of that. It'll be archived. If not, you can go to Heating Help and see an archive of that. But I'm going to make a clear plastic tank and show you how this flow goes through a buffer tank. So this is what's called a 4-port buffer tank. Got to find a tank, obviously, with 4 connections like this. Be nice to have a connection on the top for your air vent, maybe some additional connections for temperature sensors that you could put in the well here. These tanks are available out there in different sizes. I think you can get them as small as I think Boiler Buddies go down to like a 25-gallon size, and you can usually find them up to 120 gallons or large. I mean, you can build them as large as you want, but typically off the shelf, you can find somewhere between 20 and 120-gallon buffer tanks and sizes in between there. Now here's you can make a hydraulic separator, and here's a few examples of pictures that people sent to me of hydraulic separators that they built themselves. And what I like about both of these, they wanted a corner-mounted hydraulic separator, so they said, is there any reason that I couldn't, go on one side of the separator and go out at a 9-degree to that as opposed to straight across from one? Yeah, and sure you can. And they don't have to line up. The 2 at the top don't have to be straight in line even if you went straight across. So here's an application where it worked out. They could mount it nice and cleanly in the corner, still have hydraulic separation on their A and B side. This one's made out of probably an Aquatherm brand, maybe, of a PP type of pipe that was just fusion welded together. If you are going to make your own, now you may or may not be able to put a median here and make a nice air separator and dirt separator out, but pay attention to that 3-to-1 relationship. If that's going to be I don't know, let's just assume that's a 2-inch pipe, I would want to have a 6-inch. Now you can, you've got a little bit of wiggle room there. I won't say that it absolutely won't work if you were a size off on the center tube, but to assure the lowest possible flow velocity from the top to bottom of the separator, keep that 3-to-1 relationship. Another thing I will say, when we get into the really large separators, maybe a 6-inch diameter pipe size and up, we engineer the size of this. The relationship, that's a rule of thumb. That 3-to-1, I would say up to a 2-inch pipe size, that's a pretty good rule of thumb. But when you start talking 4, 6, 8, we go all the way up to 12 and 14-inch pipe size separators. That's not a 3-to-1 relationship anymore. We don't end up with a 12-inch pipe and a 3-foot diameter pipe, and a 12-inch and a 36-inch diameter center barrel. It's a little bit smaller because there is actually an equation that you can size that to get that that relationship right for the flow velocity in that center tube. This one here, this fellow I know is a welder that works in the food process industry up in the St. Louis area, and you can see he's welded up and used a flange type of connection in the center there with a band that he can get inside there and clean it out or work on it if he had to. But it was a nicely built application. I've seen him build out a copper tube. I think Bob back in back in Massachusetts, some of you guys know Bob Bone makes them out of a couple Schedule 40 cross threaded cross fittings, and puts a nipple between them, puts his air vent out the top, and side branches for the primary, secondary. So again, just size them properly, the relationship of the branches to the tube in the center, and they're going to work fine for hydraulic separators. And they can be put on their side. They don't have to be vertically like that. I want to point you to a couple references. A lot of the slides that I use today come out of one of these 2 hydronics issues. It's not a sales spiel here, but we offer these to the industry for free. These are really technical journals that show concept, that show applications. It's really not intended to, in fact, you'll see Taco products in here. You'll see Bell & Gossett pumps and products in these journals. They're really not about Cluffy components per se. It's just to explain to the industry, how to pipe systems together so you don't have problems. And this one here, I use this for beginners, but to be honest with you, before I go out on a training event, I'll keep one of these in my bathroom and I'll read it when I'm in there just to get back to speed. I can't remember all this stuff, keep it all straight in my head anymore. So this is, even if you're a seasoned pro with boiler piping or primary, secondary, or whatever your trade might be, this is a good refresher every now and then, or for your apprentices, I would recommend this to them. And this is the one, any of the pictures that I showed you today that have an X through it come out of this issue, number 19 of Hydronics, that we did, 2016, I guess we did that. Basically what we did is we've taken the most common piping mistakes that we see out there, and we just show the correction for it, how to take a drawing that's got the X through it that was piped properly. What's the fix for that? How can I reconfigure that piping so it'll work? So a lot of good information in here on both piping and wiring, actually, on how to wire up a complex system. So these are available for free. If you get a hold of us at me or contact Cluffy directly, we can get you hard copies. If you like hard copies, I do. I like to make notes in the margins of these. These are also available at the Cluffy website as a PDF. So if you want to download that and use those drawings for building your own schematics and stuff like that. We are starting with issue number 27, which will be July of this year, 2020. We're going to have a digital version of it. That's one where, you can kind of page through it. You click on the little arrow and it's just like you're reading the book, but it's on your computer. So we're thinking that might be friendly for the generation that embraces doing everything on a computer instead of a piece of paper, which is fine. I'm learning that habit too. So let me know if you need help getting these, or if you want some of the back issues, we can find some of those for you and make these available to to anybody that's watching this or gets to see this. So obviously I can't open it to a question and answer here, but I think that's pretty much what I had. So hopefully there was some information in here that you've learned some new ideas, some other options for piping systems, whether you want to stick with your primary, secondary with your home built tees, or if you want to start looking at your options for hydraulic separators. We do have a separator. I will put in a little plug for a Cluffy Sep 4. And what we did with a Sep 4 is, in addition to having the separation, the air removal and the dirt removal, we put a magnet in the bottom of it. Now, I don't know if I got a picture of one here. We stick a magnet in here, so if you have any fine metal particles, magnetite is typically called, that could get into some of the permanent magnet type of wet rotor circulators that are showing up everywhere on the market now. It gives you one more protection level. Just it'll get a small particle that you can't get out with a Y strainer, that you can't get out with a dirt separator. It's just a little magnet that goes up inside the tube here, and then you pull the magnet out, the metal particles fall off the magnet, and then you open this ball valve right here and flush them out. So now you've got air separation, microbubble separation, you've got dirt separation for the big chunks, you've got magnetic separation for the particles under, say, a 5-micron particle. It's pretty hard to pull out with a strainer or a mesh, but you can pull that out with a magnet if it's a ferrous metal. So consider that also. I think, to make a long story long, we've gone through pretty much all of these. There are other piping configurations. I would like to encourage you to look at some of the 2 and 3 pipe buffer piping arrangements that are out there now. They add a little bit more, I don't want to say value or opportunities with the different configurations to save you some piping and save you some expensive tanks that these 4 ports can be. So we'll have some videos and YouTube videos parked on the different buffer pipe configurations also. So I'd like to thank the EEE for making this available this way for everybody that couldn't attend this year. And love to hear your stories or what you have going on in there, anything you can share, any lessons that you've learned. Certainly don't know it all. I'd like to learn what's going on in the field. I don't get out there as often as I'd like to anymore, pulling the wrenches, but I'm always interested in seeing what everybody else is doing with the components, with their system. So shout out. I'm all over the social media. Cluffy is, I am. Hard to hide these days in this digital world. You can be found. So thanks again, everybody, for showing up. Thanks to everybody that's going to watch us in the future, and hopefully next year we'll get together again somewhere at the Eastern Energy Expo event. So bye bye, everybody.